Strap on your seatbelts and get ready for a ride through space and time because we're going to explore the wacky world of general relativity. So, what is general relativity? In a nutshell, it's Einstein's theory that explains how gravity works. But before we get into the nitty-gritty, let's take a step back and talk about what gravity is in the first place. You see, back in the day, people thought that gravity was just a force that pulled objects towards each other. But Einstein came along and was like, "Hold up, everyone. What if gravity isn't actually a force at all?" And the people were like, "What do you mean? Of course it's a force. We learned that in school." And Einstein was like, "Well, yes, but actually no." Here's the thing. According to general relativity, gravity is actually the result of objects warping the fabric of space-time. Picture a trampoline. If you put a heavy ball on it, it'll create a dip in the surface. Now, if you roll a smaller ball nearby, it'll get pulled towards the larger ball because of the dip in the trampoline. That's kind of what's happening with gravity. Massive objects create a dip in space-time, and smaller objects get pulled towards them. But it's not just mass that warps space-time. Energy and momentum do too. This means that light, which has energy, can also be affected by gravity. In fact, one of the coolest predictions of general relativity is that light can be bent by gravity. This was first observed during a solar eclipse in 1919, when astronomers saw that the position of stars near the sun had shifted slightly because their light had been bent by the sun's gravity. Now you might be thinking, okay, but if gravity isn't a force, how come we feel it as a force? That's a great question, my friend. The answer lies in the fact that objects follow the shortest possible path through space-time, which is called a geodesic. When you stand on the ground, you're following a geodesic through space-time, but it feels like you're being pulled towards the Earth because the Earth's gravity is warping that geodesic. So that's the basic idea behind general relativity. Gravity is the result of objects warping space-time, and everything moves along geodesics through space-time. But there's more to it than that. One of the other mind-blowing predictions of general relativity is that time itself can be affected by gravity. Here's the deal. Time isn't actually separate from space. They're both part of the same four-dimensional fabric of space-time. And just like mass and energy can warp space-time, they can also warp time. This means that time can run slower or faster depending on how strong the gravitational field is. To understand this, let's go back to our trampoline analogy. Imagine you're on the trampoline with a friend and you each have a stopwatch. You start at the same time, but you're standing on the edge of the trampoline while your friend is standing closer to the ball. Because you're farther from the ball, you're not experiencing as much gravitational force, so your stopwatch runs a bit faster than your friend's. This means that when you both stop your stopwatches and compare them, your friend's will have run slower than yours. This might sound like a weird and abstract concept, but it's actually been confirmed by experiments. For example, atomic clocks that are placed at different heights in Earth's gravitational field run at slightly different rates. The one closer to the ground runs slower because it experiences a stronger gravitational field. Another cool thing about general relativity is that it predicted the existence of black holes. Black holes are massive objects that are so dense that they create a gravitational field that's strong enough to trap even light. This means that anything that gets too close to a black hole, even light, can't escape. Black holes might sound like science fiction, but we've actually observed them in the universe. We can't see them directly because no light can escape their gravity, but we can observe the effects of their gravity on nearby objects. For example, if a star is orbiting around a black hole, we can observe the way its light gets distorted as it gets closer to the black hole. So, that's the gist of general relativity. It's a theory that explains how gravity works by describing the way that massive objects warp the fabric of space-time. But, as with any scientific theory, there are still unanswered questions and things that we don't fully understand. For example, we still don't know how to reconcile general relativity with quantum mechanics, which is the theory that explains the behavior of particles on a very small scale. General relativity works great for big things like planets and stars, but when we try to apply it to tiny particles, things start to get weird. One of the funniest and weirdest consequences of general relativity is the phenomenon of time dilation. Basically, if you're moving really fast relative to someone else, time will appear to pass more slowly for you. This means that if you were to go on a spaceship and travel close to the speed of light, when you come back to Earth, you'll have aged less than everyone else. This might sound like a great way to stay young forever, but unfortunately, it's not really practical. Another weird consequence of general relativity is that the universe is expanding. This means that galaxies are moving away from each other at an accelerating rate. The reason for this expansion is still a mystery, but it's thought to be related to the fact that the universe is filled with a mysterious substance called dark energy. In conclusion, general relativity is a theory that describes how gravity works by explaining the way that objects warp the fabric of space-time. It's a mind-bending concept that has led to some of the coolest discoveries in astrophysics, like black holes and time dilation. But it's also a theory that raises more questions than it answers, and there's still a lot we don't fully understand about the universe. So, strap on your thinking caps, and let's keep exploring the mysteries of space and time together.